The dynamics course in a typical engineering program is an expansion and an extension of the concepts and topics covered in the physics course related to objects in motion. Depending on the level of difficulty of a physics course at either the high school or the university level, and depending on whether or not that course already included mathematical tools like derivation, simple separation of variables, and simple vector algebra, the dynamics course will have fewer or more new topics compared to what you're already familiar with. The dynamics course is usually a prerequisite for other engineering courses like vibrations, control systems, machine design, and advanced or multi-body dynamics. Its prerequisites often include calculus, linear algebra, and statics, or mechanics 1. The course content and sequence of topics heavily varies depending on the instructor or the textbook they follow. So look at the list of videos for this course in the description of this video, and I'll try my best to title the lectures in a way you can easily cross-reference them to what you are covering in your class. The overall general core topics include kinematics, which focuses on studying the motion of an object without taking into consideration the forces that cause it to move, kinetics, which does take into account those forces, work and energy, and impulse and momentum. And each of these can be separated into two categories. Particles, which means we think of all bodies as point masses that occupy no space and therefore things like rotation are neglected, and rigid bodies, which means these bodies do occupy space and therefore things like center of mass, moment of inertia, and rotational motion are important. We call them rigid bodies because we're assuming no deformation. Motion of deformable solids is most typically not a part of a dynamics course. The progression of the course topics could therefore be kinematics for particles and then right after kinematics for rigid bodies, then kinetics for particles and right after kinetics for rigid bodies, and so on and so forth. Or alternatively, you could do all topics for particles, from kinematics to impulse and momentum, and then start over from the beginning of the list of topics for rigid bodies. This playlist of lectures will use the former option. We'll be switching between particles and rigid bodies as we cover the main topics, and we'll include all subtopics and concepts for each one of these as we go. Now for the connection between these topics to make sense without deviating too much into prerequisite concepts review as we cover them individually, it's important to really master basic vector algebra, differentiation rules, and statics. Specifically, it is very important to be able to, without any hesitation whatsoever, find the components of a vector, find the magnitude and direction of a vector from its components, understand unit vectors and rotated reference frames, perform common dot product and cross product calculations, both with variables and values, differentiate using chain rule, product rule, and quotient rule, solve the simplest of differential equations using separation of variables, draw a correct free body diagram, and calculate a moment due to a force using vector notation. And again, do all of this without 1. Spending too much time, 2. Hesitating what to do next at any step, nor 3. Making small mistakes that will lead to an incorrect final answer. So to that end, we'll focus on very quickly reviewing these topics in the next few minutes, with several sub 3-minute example videos linked in the description of this video for each one of these topics, to practice what we review here today. Remember, this is only a quick review, not a deep dive into each one of these topics that I just listed. Let's begin with vector components. If we have a 2D vector of magnitude p at an angle theta, and we want to calculate its Cartesian components in the I hat horizontal and j hat vertical directions, what we would do is multiply the magnitude by the cosine for the horizontal component and the sine for the vertical component. Of course, this is for a given angle theta between the horizontal line and the vector itself. If the angle we're given is between the vertical line and the vector, the trig functions would be reversed. And these relationships are true for angles between 90 and 360 degrees or even negative angles. For example, a vector in the second quadrant would have a positive j component and a negative I component. The cosine of an angle between 90 and 180, the second quadrant, would itself be negative, so you wouldn't need to worry about adding a negative sign in any case. The same is true for sines and cosines of the third and the fourth quadrants. If on the other hand what we know is the components of a vector, because they are given using the vector notation, we would use Pythagoras to calculate its magnitude, And since the tangent function is defined as the opposite over the adjacent side, the angle with respect to the horizontal would be the inverse tangent or arctangent of j hat over I hat. In this case, you do have to be careful with negative signs in the components or angles outside of the minus 90 to plus 90 degree range. Notice that for a 3D vector, we can still use Pythagoras to calculate the magnitude. If you want to review more about both 3D vectors and the use of arctangent to calculate angles, you can find 2 links to these short video explanations down below. Something we often use in our kinematics analysis for this class is polar and normal tangential coordinate systems. For this reason, it's important to be able to move between reference frames so that we can go from and to Cartesian, polar, and NT coordinates easily. So for example, if we know that the u hat v hat frame is rotated an angle of theta from the I hat j hat frame, we should be able to find u hat and v hat in terms of I hat and j hat. The u hat vector would have a component equal to 1, the magnitude of a unit vector, times cosine of theta in the I hat direction, and 1 times the sine of theta for the j hat direction. The v hat vector would have a component of 1 times sine of theta in the I hat direction, pointing to the left, and therefore with a negative sign, and 1 times the cosine in the j hat direction. And this one is pointing up, so no need to add a negative sign. Cross products are a lot more common in dynamics than dot products, but let's review both. The dot product between two vectors a and b is algebraically defined as the sum of a sub I times b sub I. So the dot product of two vectors is a scalar, or in other words, just a number, not a vector. If a is, for example, minus 1, 4, and 3, and b is minus 2, minus 1, 7, the dot product would be the number 19, a scalar. Geometrically, the dot product is the multiplication of the magnitude of the component of both vectors in only one direction. This means that the dot product can also be expressed as a times the component of b in the direction of a, or b times the component of a in the direction of b. Either way, we end up with magnitude of a times magnitude of b times cosine of theta. The cross product is simultaneously defined algebraically and geometrically as a times b sine of theta, pointing in the normal direction to the plane that a and b make. In other words, the cross product yields a vector because it has a direction, and that direction is perpendicular to the plane created by a and b. We follow the right-hand rule to determine the normal orientation. Common uses in dynamics include understanding the following list assuming perpendicular vectors I, j, and k. You can check these results yourself by practicing the right-hand rule. There is a matrix-based representation of the cross product and the use of a determinant to calculate it, but we don't use that in dynamics for the most part. The product rule for differentiation tells us that the derivative with respect to x of f of x times g of x is equal to f of x times g prime of x plus f prime of x times g of x, where the prime denotes a derivative. So for example, the derivative of x squared times sine of x would be x squared times cosine of x plus 2x times sine of x. More examples of this and other differentiation rules are found in the description below. The quotient rule refers to two functions within a fraction, and it tells us this, where again, the prime nomenclature refers to derivatives. And finally, the chain rule, used extensively in dynamics, tells us that if there is a function within a function, f of g of x, like for example sine of x squared, its derivative is the derivative of f times the derivative of g. A proof of all of these and plenty of examples are linked down below. This is commonly used in dynamics when we have a function of a variable that is not time, t, and we are differentiating with respect to t. For example, if we have a function that defines the position of a particle as x cubed plus y squared equal to 10, and we are differentiating with respect to t, the derivative would be 3x squared, which is the derivative of x cubed with respect to x, and we still need to multiply this by the internal derivative of x with respect to t. We'd do the same for the second and the third term to find this expression. We'll frequently use the equations a equal dv dt, v equals ds dt, and a ds equals v dv. Depending on how s, v, and a are defined, we can end up with variables and infinitesimals on opposite sides of the equation. For this reason, it's important to be able to easily apply separation of variables to solve these simple differential equations. As an example, if we have dy dx equal to 2xy, we would divide both sides by y and multiply both sides by dx to obtain 1 over y dy equal to 2x dx. This would allow us to integrate 1 over y with respect to y and 2x with respect to x. And this is it for a quick review of topics you'll use for dynamics. These videos usually end with a short example that applies everything we've learned in them, and more example videos are linked in the description below. However, because this video is a summary of a review of topics, I won't end this video with a general example. I will leave you only with the linked examples for each one of the topics we reviewed here today, and you'll find examples for free body diagrams there as well, since we didn't really include that here as part of the math summary. Make sure to check out all the links in the description of this video, and I even have links to playlists of other engineering courses there as well for you to check out. Thanks for watching!